So the process we recommend for our early adopters in Coreform Flex for setting up their problems, let's call this AM FinStock, is to start by creating a procedure. So in this case, I've created this procedure where I just want to compute the stress on this model, and I've chosen a solid mechanics um, physics application here. Um, and then the recommended workflow is that within your solid mechanics procedure, or whether you're doing heat transfer or modal analysis, is that um, there's the flex model, which is the assembly of individual parts that might exist, and assign to each part materials, define the interval for your procedure, assign time stepping methods, your boundary conditions, load conditions, so really defining the problem. And as you work through this procedure, it'll take you to different parts of the model tree. This is something that we are improving in our latest development versions from a user experience perspective. Um, but I'll just work through or walk through some of these individual steps here. So the first thing we've done is we've added a flex model where we've defined the part that we want to have in our assembly. So we want this fin stock and a material and its material model. Notice that in this material that I've used, I think this may not have updated, but I've used an elastic material model, which is the elastic material model is a small strain assumption um, that I have assigned to this. Um, so that's the material for this. Again, I could change this if I wanted to say like 36. Um, but if this is aluminum, then it's going to be probably like closer to 10E6. Um, as you finish your materials and assign them to the parts, um, there are some additional options that there are good defaults for, but we don't necessarily recommend changing. After defining your flex model, you define your interval. Here I've got a run interval that I've assigned, um, which runs to a time of just one. So this is going to be a linear static solve. I don't need to have any sub increments. I can just solve it all in one go. Next, we'll talk about like just the time steppers. Again, I mentioned this is going to be a linear problem, but for any given time steppers, we support in our beta functionality some nonlinear time steppers. So a continuation method, which is a implicit nonlinear static method, as well as implicit dynamic methods that are based on generalized alpha, and explicit dynamic methods based on central difference method. Um, these solvers are all fully parallelizable. The linear solvers that are even used for the nonlinear approaches of the implicit dynamics and implicit statics use direct solvers that are provided um, by a fully parallel high performance computing library. So you can run these problems on multiple cores for improved performance. The next thing that you would do is you would assign your boundary conditions. I've already done that here, but what I'll show is that what's important to do is to assign sets. So we have a set manager. We're able to come through and assign or select surfaces or volumes, curves that are involved in a given condition. So if I wanted to say change this boundary condition from being an X symmetry to maybe I want to hold the top of this volume, I can just change my surface selections. I can also change the name. So maybe I want to hold top surface. Um, and then I'll just, for the individual boundary conditions themselves, that surface that's in the boundary condition has automatically updated to be this hold top surface. We also have then the ability to choose, um, say, all these internal surfaces. We can select, I'm going to clear this set out here real quick, just so you can see this process. The ability to um, let's, I can select the entire cavity, which will speed up the selection of set entities, and then I can choose to select continuous to get more. You can see there's some of these surfaces that maybe don't get selected, and so then from there we can select. There you go. got all those surfaces from that continuous selection. So that saves us, as you can see, a lot of button clicks that would otherwise have to be done manually to select all of those surfaces. So you can see here, the actual simulation we ran, we'll go and we'll look at the results. But I did run with the X symmetry as opposed to the top surface. We also then created a load condition, which is just an applied pressure on the internal surfaces. Um, and the options we had for those load conditions, um, uh, we could do like surface tractions, pressures, body forces, line tractions, but we've chosen to use a surface pressure here that takes a function, in this case, a constant value, and then we just scale it by 350 so that to have a 350 psi load on those internal surfaces. Um, then what we also have is we have our outputs, um, and we have outputs on both a probe where we can probe along a line. So we can probe a field value along this line. So in this case, pick two locations, request 200 points, and then we want to get off the stress values of those points. We can also choose to request the maximum von Mises stress, so an extremum value in that field. So a maximum von Mises stress. And then at the location of that maximum von Mises stress, I can not only report the max von Mises, but say I wanted to report the magnitude of displacement at that location. I can query those values as well. What's important to note with both of those is that those are, again, completely independent of the mesh that I'm using. I don't have to make sure that they align to nodes or anything. I can just pick arbitrary locations to query and then change the mesh as I want. And so that's another just workflow improvement that Coreform Flex provides to users. And then we just request those probes as results. We also then have field output. We currently view our results in peer review. And that's what I'll show next is just show these results in peer review.